have to make a z in the interior. Right? So I have to make it a z simple in the very beginning, which means before I even use polar coordinates, I have to switch this order, dy, dx, dz to dz and whatever. All right? So I have to have dz in the interior, which means I have to switch between the 6 representations first. And that, in most of cases, is not easy. Okay? In that, most of cases, you do have to sketch the solid region as the intervening region in R3. Okay? But this problem is actually much easier. You don't have to do it for the following simple reason. So y is simple here, right? So this is a y simple in the space, x simple on the xz plane. So y is bounded between two functions of x. It is independent of the z. And if you look at the restriction on z, z is only bounded between two numbers, which means if I switch the order from dy to dz, I don't have to care about the z variable at all. Okay, so what I'm saying here is I can simply rewrite this as from 0 to square root of 2, from x to square root of 4 minus x squared, from 0 to 6 e2 minus x squared minus y squared dy dz dy dx. I can simply do the following, for the following reason. Z is bounded by two numbers, and the relation between x and y is strictly between themselves. They have nothing to do with z. Okay? So when I switch the order, I'm not gonna have two functions of x, y anymore. Imagine if you have two functions of x, y. That means the solid region as the intervening region. When you define the functions, the boundary functions will have the relation between x, y, and z. All right? If you do have two functions, here you have a function of x, y, you have a function of x, y here. That means the boundary functions will have the relation between x, y, and z. Am I right? But that is not the case. In the very beginning, z is bounded between two numbers, and the boundary functions are strictly between x and y. Am I right? Has nothing to do with z. Are with me? So when I switch the order, I cannot have the relation of z to depend on x, y. Are with me? That's one way to understand why I'm doing here. But the strict way of doing this switching is to sketch the graph. So I do want to challenge myself to sketch the curve and see why this is the case. And I strongly recommend you to do the same. Okay? So here I have z is bounded between 0 and 6. X is bounded between 0 and square root of 2, and y is bounded between x and square root of 4 minus x squared. So in the following, you will definitely refresh your memories about a lot of objects we have been talking about the whole semester in the space. Okay? So my z is bounded between 0 and 6. Let's see, this is my 6. Again, you don't have to be super precise about the units and everything, but we have to at least know the key information. X is bounded between 0 and square root of 2, so basically it's right here. Okay? Now y is bounded between x and square root of 4 minus x squared. I have to know what one boundary function is. X is equal to y, and the other boundary function y is equal to the square root of 4 minus x squared, right? So these are two boundary functions. Let's make it consistent. Y is equal to x. What is y equals x?
A line.
A line on an xy plane, but in the space it's going to be a plane, yeah, right? Again, linear function in xyz in the space is definitely a plane. So, and it is a line, and that line is passing through 0, 0 with radius, with slope 1 on the xy plane. So this is the xy plane, and it is going to be a plane looking at this. So if you have this vertical plane to intersect with the xy plane, that straight line is exactly x equals y on xy. All right? You with me? So this is going to be a plane cutting through the z-axis, cutting through containing the z-axis, and when you see it's a vertical intersection with xy plane, this is exactly x equals 1. And this one is the same. When I have y equals 4 minus x squared, I know on the xy plane it's going to be x squared plus y squared is equal to 4. All right? It is going to be a circle, but only a half of a circle, right? So y is positive. I only have a half of a circle with radius 2. So this is square root of 2. Let's say this is square root of 2. So the 2 is going to be right there. Okay? So this is the half circle on the xy plane. But again, this is not an xy plane. This is defining a surface on xy space. All right? You don't have the z variable in here, so it's going to define what's the word I'm looking for? This guy defines a cylinder. All right? You don't have a variable, then you can just simply pull in that variable. So you gotta get a whole this is going to be the cylinder right here. Okay? This is the cylinder right here. Okay, so now I can sort of identify where my intervening region is. This intervening region is that if you project everything back onto the xz plane, you're going to get this right angle. All right? If you project everything back to the xz plane, you're going to get this product of two intervals, which is the definition of the right angle. So this is the right angle if you project. And then it is bounded between this one and the circle right here. All right? So if I'm looking at what the projection is on the xy plane, it's going to be this region. Okay? So if you can imagine, I have a plane right here. I have a cylinder on the above. And the integrating region is the solid upon this right angle and bounded between a plane and the cylinder. Okay, so this is the region right here. Okay, so making this simpler, it's going to be from here to here. Okay. So this is the plane. Okay, this is the plane, and this part is the cylinder. And between this plane and the cylinder, built upon this right angle, is going to be my solid right here. Okay, that was me. So if you have a three-dimensional imagination, this is going to be the solid region as the intervening region. Okay, so this is a y simple in the space, and then x simple in the. Sorry, in the very beginning is a y simple. Yeah, it's a y simple in the space, x simple on the xy and xz plane. And if I want to identify it as a z simple region, I need to look at its projection onto the xy plane, which is this piece. All right? Mm-hmm. This is the projection onto the xy plane. And then I need to look at the boundary functions for z, the lower function and the upper function. And you can immediately see the lower function is exactly z equals 0 and z equals 6. It has nothing to do with x and y. Mm-hmm. All right? Has nothing to do with x and y. So z is bounded between the lower bar and the upper bar. And this region is where I need to identify. Okay? Again, one way you can understand this is what I explained right here. You can switch the order of z with x and y directly. Because in the very beginning, my boundary functions only involves the relation between x and y. Z is not in there. So when I switch the order here, I cannot have functions depending on x, y here. Otherwise, I will have the relation on the boundary between x, y, and z. The other way you can convince yourself is you simply draw or sketch what the region is. Okay? Mm-hmm. Now, as long as I'm convinced here, I'm convinced I can do the following. Okay? Are you convinced? Yeah. Well, sort of, right? 80%. Then you need to fill the other 20% after class. So the next step is still pretty interesting here. Okay, listen to me careful. Okay, listen to me careful here. Okay, I have sketched the graph for the solid region over there. And next, I need to identify x, y as a polar region. I'm not going to go to that picture. That picture is not very subjective. It's not very informative. It is in R3. And we already did exactly the same thing here. When we identify x, y as a polar, we don't go to R3. Remember this closely. Don't go to R3 in order to see how I can identify this region as R and C region. It's pretty challenging, and sometimes it's going to give you the wrong information. Go strictly to x, y, and draw a separate picture. That was me. And when you do that, you can have a much more precise picture. So I'm going to forget about this. And this is only used in the very first step. And next, what I'm doing is strictly with respect to x and y. And this is so crucial that when you deal with cylindrical coordinate system, always identify this region strictly with respect to these two pieces of information. Strictly with respect to these two. Okay? Forget about z. Don't deal with z when you do r and theta. So now let's see what we have. So when we do that, we have am I making any mistake? Not really, no. So x is between 0 and the square root of 2. So 0 and the square root of 2 right here. Y is between y equals x and y equals x and y equals square root of 4 minus x squared. I know one of them is a straight line passing through the origin with slope 1. Okay? The other one is x squared plus y squared is equal to 4, so it's going to be a piece of circle with radius 2. So it's a piece of circle with radius 2. And it is bounded between y equals x and y is coming from this part of the circle. So it's going to be this region I want to identify. Okay? This is the region I need to identify in the xy plane. Are you with me? So if you compare my picture right here and the picture right here, all right, you can immediately see this one is much easier for you to translate to r and theta. You don't go to R3 all the time. This is only used when you go for the first step. Okay, when you identify x, y to r and theta, always draw the picture in xy plane strictly, involving no z variable. So now I need to identify two angles and two radii. The radius is pretty easy to find, 0 and 2. The angle is this angle to that angle. All right? The greater angle is definitely pi half. The smaller angle is pi over 4 for the reason that it is contained in this, what is the English word I'm looking for, isosceles, right? So this is the radius 2, this is square root of 2, so this has to be also square root of 2. So this angle and that angle are both pi over 4, all right? That was me? So this angle is pi over 4. So it's going to be from pi over 4 to pi over 2, from 0 to 2, from 0 to 6. Remember, when I do the interior, okay, I need to switch between x, y to r and theta again. So it's going to be e2 minus r squared dz r dr d theta. Okay, that's the most challenging step. Okay, that's the most challenging step, and as long as we can accomplish that, the following work will be much easier. Okay, I need to find the antiderivative where z is the variable. So from 0 to 2, so z is the variable, so this whole thing is constant. So it's going to be z2 minus r squared multiplied by 6 multiplied by r, and then dr d theta. You can do the following. Okay? So when I eliminate the variable z, I'm getting 6e2 minus r squared, and then multiply by r, which means this function has a pretty easy antiderivative. Okay? So you can do the following. Any questions about cylindrical coordinate system? Okay, so I want to finish this discussion about cylindrical coordinate system by one more example. So this is the one. I want to find the volume of the solid, okay, of the solid bounded by z is equal to 2 square root of 5 and z is equal to square root of 16 plus x squared plus y squared. Okay. I want to quickly ask you what they are. Z is equal to square root of 5. What is this in our case? Horizontal plane which passes through 0, 0, 2 square root of 5. Right, so this is the plane parallel to xy plane. What is this guy? So if you don't like the square root, it's going to be z squared is equal to 16 minus x squared minus y squared plus. So it's going to be z squared minus s squared minus y squared is equal to 16. This one is, what is this? Right? It's not that long time ago that we're so smooth about it. This is a hyperboloid, definitely, with two sheets, right? Separated by xy plane, all right? Separated by xy plane for the following reason. I give you this intersection and the traces identification quickly. It's not going to intersect with x-axis. It's not going to intersect with y-axis. There's no intersection with the xy plane at all, so it's definitely separated by xy plane. So this is only a hyperbola with two sheets, and because in the very beginning I have z is equal to square root of this thing, so it's going to be one sheet, one of that hyperboloid. So it's going to be pointing upwards, and this is the, and then it passes through. I'm sorry, it is bounded by z is equal to 2 square root of 5, and I can easily